this off my 10 minutes?
I'll start it.
That's if I ask. That was what I had to do.
You're gonna have to sort of stand over here or walk over there and hit the keyboard.
Okay. Let me see. As I said, 10 minutes in the dark. This is about dark matter and dark energy. I'm from WVU Parkersburg, which is just a very small branch of the big school WVU. What do I do?
Just hit the button.
Return.
And return. Enter. There we go. Okay. Abstract dark matter and dark energy can be explained using a single extended model of space-time continuum. Cold dark matter halo around galaxies is nothing but pure spatial curvature, no machos, no other particles, no quantum mechanics, it's just pure general relativistic. And I use a simple, very, very simple four-dimensional extension to explain this, and then once dark matter is explained, dark energy follows. It gives a complete explanation of dark energy. This requires no changes to general relativity, no changes to any physics, except one, that is acceptance that space-time curvature is extrinsic in a macroscopically extended fourth dimension. We're approaching crises in physics. The scientific community is presently faced with two serious anomalies that are rapidly evolving into crises, dark matter and dark energy, and that's not my words, that's generally understood. It has become practice to solve these problems independently, even though it's commonly believed that they must have a single solution. If you just accept E equals mc squared, it makes sense they have a single solution. However, it is usually simpler to find, it's actually simpler to find a geometrical solution, the cold dark matter, the halos around galaxies, spiral galaxies, and then use geometry to demonstrate the presence of dark energy. The solution to both is straightforward. All you need is a macroscopically extended fourth dimension. In GR, classical interpretation is the curvature is intrinsic to the space-time continuum. However, the universe can also be modeled using a positively curved three-dimensional Riemannian surface within a four-dimensional embedded space, evolving in time, or a five-dimensional space-time. If you're talking about evolving in time, you're talking about four-dimensional space. Otherwise, you're talking about a space-time, five-dimensional space-time. Models that require an extrinsic curvature in a higher dimension are completely compatible with GR, general relativity, and the idea of a higher dimensional embedding space with extrinsic curvature is actually normal. Just go to gravitation by Mesmer's Thorne Wheel, where they talk about it quite a bit. So I'm not doing anything out of the ordinary. The Einstein rays of the, that's R sub E. Your version of PowerPoint does not follow mine. That was the sub of the original. It's so large that global curvature is nearly flat on the local scale. Global curvature of anywhere from 10 billion to 13.7 billion light years. We don't know exactly. At least no discrepancies between global curvature at the local level and local curvature from a local gravitating object, say the sun or the earth, can be derived or tested. Gravitational forces on a very small scale are insignificant, as is the global curvature. So, of course, global curvature has nothing to do with atomic structure or molecular structure. On the other hand, the curvature of space-time on the local astronomical scale, say within a star or a star system, is masked by the local curvature of the massive body. However, once you get past the solar system, you're talking about a spiral galaxy, more complex stellar structures that are very large on the astronomical scale. This would not necessarily conform to the overall positive or global curvature of the universe. So if the universe is five-dimensional, the fifth dimension is space-like and macroscopically extended, both the halo surrounding spiral galaxies and the increasing rate of expansion of the universe could be accounted for as a difference between local material structures and the global Riemann curvature. It's very simple to show. A galaxy grows three-dimensionally outward beyond the positive curvature of the universe. This is positive curvature. A galaxy starts growing from the center outwards. And so the curvature of the galaxy as it grows from the central core, the mass in the central core totally masks the curvature here. But as it grows outward, The global curvature is not strong enough to pull it down to that surface. In galactic formation, it's commonly accepted fact that matter curves space-time, not the reverse. So the very slight overall curvature of space-time is not strong enough to pull the growing galactic plane of matter down to the surface of the positively curved universe as a galaxy forms. As a galaxy grows outwards from the three-dimensional gravitational center or core, the halo also grows in direct proportion along the increasing radius as it gets larger and larger. There's a bigger gap between the overall curvature and the galactic plane, which is three-dimensional. At least until the building or material accumulation phase of the galaxy is complete and the radius stabilizes at roughly constant value. The halo forms around the galaxy. The galaxy decides it's on three-dimensional. There's gravitational electromagnetic forces in the galaxy that decide it's three-dimensional, not the three-dimensional global curvature. And the three-dimensional global curvature can't pull it down, so it grows out like this. Yet it has to remain continuous with the rest of the universe. So in a sense, it pulls, as it's growing, it pulls the universe up to it, that global curvature, up to it. And that introduces a small dimensional gap. I've calculated that gap for Andromeda at the far edge of Andromeda, which is a few 100,000 light years radius. The gap would be a half light year right here, just using Pythagorean theorem. That's all you need. You have to have three-dimensional conformity between the galactic plane and the overall universe. The galaxy must remain three-dimensional within its own material self, according to its own internal forces and fields, but it must also appear to conform to the three-dimensional curvature of the universe in general, such that the rotational plane must remain continuous with the rest of the universe, thus producing a physical discrepancy or a dimensional gap. In other words, this discrepancy can only be overcome if the curvature of the universe bends toward the higher dimensional plane. Now, this is what astronomers observe. This is what we all observe. We observe the galaxy as if it's pulled down to this plane, and that leaves the halo around. Because we're seeing it through our own three-dimensional curvature from our own observation post after three-dimensional curve. This model predicts there should be halo without observing it. If it hadn't been observed, this model would predict it. According to the theoretical model, astronomers should detect an unspecified, normally unsuspected halo of space-time curvature around three-dimensional galaxies of sufficient size. Sufficient size being that they are much larger than the gravitational attraction in the core, from the core material. In other words, this model would still predict the existence of halos, had we not observed them. This fits the pattern. If we take the gravitational contribution from the core outward to the speeds, you have a simple curve, 1 over r squared. Whereas this, the dimensional gap, would graph as a straight line. You add the two together and you get a curve like this. This is for Andromeda. That's the curve for Andromeda. You can see how the two would add together. And this is out of a recent textbook, 21st Century Astronomy by Hester and friends. And this is, doesn't say which galaxy this is for, but it shows enclosed mass of dark matter being a straight line from zero out to the edge, just like my model predicts, except for this little blip right here. And that would be where the strong gravitational or strong curvature due to the core masks this straight line. Now, dark energy is predicted from this model. This model predicts the expansion rate of the universe is undergoing a period of increase. The increase occurs during the mature and old age phases of a galaxy's lifetime after it stops accumulating matter, after its radius is established. From that point onwards, it's leaking dark energy back to the universe. Conversely, the expansion rate must have been increasing or slowing at an unprecedented rate during an earlier period in the history of the universe corresponding to the galaxy building phase. Universe expands outwards over time to close the gap. Here's the galactic plane, four-dimensional space. Here's the halo. But the universe is expanding outward to fill that gap. Now the height of this gap is the dark energy that controls galaxy formation. Because it's proportional to the potential, the gravitational potential that it adds to the system to keep the rotational speeds constant. But the universe is expanding outward, closing that gap very, very slowly over billions and billions of years, closing that gap. Conservation of energy, the energy has to go someplace and it leaks back to the universe.
You can finish up in just half a minute.
Okay, so as the universe expands, that dark energy leaks back to the universe. That can be calculated quite easily. If I'm just given the total number of galaxies, their radii, their amount of matter in them, I should be able to calculate very simply how much dark energy is going back to the universe to increase the expansion. Okay, so this is completely falsifiable. Given that number, there are several other ways this is falsifiable, and I can make simple calculations using nothing more than algebra and Pythagorean theorem. Pythagoras knew more than we thought he did. Conclusions. The confirmed existence of dark matter in both the galactic halo and more generally throughout the emptiness of space between material bodies offers clear observational evidence of the existence of a macroscopically extended fourth dimension of space. Although this macroscopic extension was originally a hypothesis, I believe this shows the actual existence of a macroscopically extended fourth dimension. And I believe the evidence is irrefutable given everything you explained. Dark matter and dark energy in a nutshell. Dark matter is nothing more than a real extrinsic curvature of the four-dimensional space-time continuum that is not directly associated with local matter, but is a consequence of the non-local material content of the universe that determines the global curvature of the universe. Dark energy is just the field thickness of the three-dimensional space in the fourth spatial dimension.
Okay, we have a few minutes for questions.
I have to ask, first of all, I'm a novice about a lot of the stuff that's going on, but I've done a lot of reading in astronomy. Are you saying here that the expansion of the universe is essentially a galactic phenomenon and not truly a universal phenomenon?
No. The expansion of the
universe by the
universe,
localization of that galaxy.
the actual expansion is global.
It shows up globally.
Well, no, it is global.
Okay.
It's just that the increasing rate of expansion, that's what they detected. That's what they call dark energy. They're calling it a negative pressure on the expanding universe. That has to come from somewhere.
Sure.
One of the latest studies I saw is some people out in Oregon have invented a new particle called the acceleron to explain this. I mean, it's getting ridiculous. And I went to a dark energy conference up in Hamilton, Ontario this summer. And 50 different ideas. And nobody can agree on anything.
But what you're saying is the source of the expansion is
the
galaxy.
No,
They're showing up
the source of the increasing rate of the expansion.
I'm sorry, yes.
It's expanding, it's supposed to be slow.
Yeah, the creation event.
Three different things. It can continue forever,
Sure.
slowing. It can become stable
Sure.
as gravitational forces pull inwards, or it can collapse down in big
Plus
crunches,
minus or flat.
tens of billions of years. So this is just the increase in expansion.
About the fourth spatial dimension, what is the extent of it?
I calculate it to be almost, it's just the same as the other three dimensions. We do not detect it. We are confined because matter itself is three-dimensional. It's electrically constituted. Matter is on that three-dimensional plane. At that point, I go into quantum theory. Explain what the quantum is. We have our extension fourth dimensional, and the fourth dimension has an effective width, not a true width because it's continuous, an effective width which is proportional to the quantum, and that gives a definition of what the quantum is. So we're confined to that. The fourth dimension, though, is pretty much magnetic. I think there's enough in normal physics that implies the existence of the fourth dimension. You've got curl B is equal to A, curl of the magnetic field is equal to magnetic potential. The divergence of the magnetic potential is zero. That implies a fourth direction. That is also why we cannot measure magnetic potential. It exists at any point in three-dimensional space. The magnetic potential is extended in the fourth dimension, which is why we can't detect it. There is no such thing as magnetic field. So I think there are other places in physics actually that imply the existence of fourth dimension. The mathematics on this comes from a theory that Einstein, Bergman, and Barger worked on in the late 30s, early 40s. So the mathematics is already there. This has the same roots as string theory, except string theory takes Klein's interpretation of Blues' theory, 21 theory. Wipe out Klein, just use Blues' original theory. And then this explains Blues' five-dimensional theory. Which, Blues' theory, if you're not familiar with it, Blues had a fifth dimension, general relativity, and was able to derive Maxwell's equations from it.
You talk about the galaxies, looking at the plane of the galaxy, you see the halo. What happens when you look at it face on? Do you have the same?
Well, we can't get into the fourth dimension. As I said, the fourth dimension is basically magnetic potential. Material bodies can't go into that higher dimension. We're stuck on that plane. And that has some fun consequences because I can use that to explain special relativity, time dilation, and everything else. It takes on a whole new meaning here. But we can't get in, so we can never be looking down. We can extend ourselves from that plane upwards as we go faster and faster. And I use that to explain the rest of this show, contraction.
Okay, well, let's move on. Thank our speaker one more time.